My name is Leemay, and our talk today is neural networks in real life. Before I get into the gist of what neural networks in real life is, what this whole talk's about, I'll give a little bit background on myself so you all know what to expect for the next 40 minutes or so. So again, my name is Leemay. I've been working at Comcast for about 8 years or so it's definitely been a while. Most recently, I've been focusing on the personalization and recommendations team. So our goal on the personalization platform is to essentially get customers the content they want quicker and then recommend new content. So here's an example. We kind of break up personalization into explicits and implicits. So this is a form of our explicit personalization. Because you watch Game of Thrones often, we suggest the next episode in that series to watch. And then an example of implicit recommendations or implicit personalization is because you watched Last Week Tonight with John Oliver. So as you can see, I've watched John Oliver in the past, and then our recommendations platform is recommending similar content to the seed item, which is Last Week Tonight with John Oliver. So having said all of that, I do want to give some insights into what the remainder of this talk is about. It's not really a case study as to how we're utilizing recommendations at Comcast. So you're not going to hear a lot of the intricate details in our machine learning, deep learning models, or how we facilitate training and evaluating those models at the scale we have at Comcast. So this is the last and first screenshot of an X1 platform that you'll see. So the reason that I'm not really going to go into the specific details is I think case studies, and this is kind of what I would consider a case study. Case studies are really helpful, and it's really interesting to see how folks are using Cassandra or Redis or S3 or Flink or Spark to get the job that they need to get done. However, my tech stack is different than your tech stack, and I think talking more holistically about the platform and what is needed from a bigger picture, it kind of gets the point across. So having said all of that, this is a brain. A neural network in real life can be considered the brain. It's funny, when I came up with this talk, I was like, a neural network in real life is definitely a recommendations engine, or it's definitely a recommendations model. And I was like, oh man, that's actually not true. It's kind of the brain. So a lot of folks will say the way that a neural network is architected in the deep learning sense is similar to how the brain works. So to understand how the brain works, we're going to take a quick time warp to biology class. I'm not a biology teacher. It was actually probably one of the worst subjects I've ever studied or ever had to take. So bear with me here. This might be more comical than informative. So let's get into it. This is a nerve cell. This is a neuron. So neurons transmit and process data. So they have these things called dendrites, and dendrites they're kind of look like tentacles, and they receive impulses from other neurons. So these dendrites, once they receive this impulse, they carry the impulse to the nucleus of the nerve cell. You'll see the nerve cell right in the middle. And again, the whole reason I'm going over this is to portray the similarities that neural networks in the deep learning sense, how they are similar to nerve cells with your brain. So the dendrite carries the impulse to the nucleus of the nerve cell, and then we see that the impulse is then processed at the nucleus and then passed to the axon. The axon is this long branch in between the nucleus and then what you'll see here as the neurotransmitters. So the axon carries the impulse from the nucleus of the neurotransmitters, which then passes the impulse to target neurons. Obviously, this isn't exactly how it's done. This isn't exactly how our nerve cells work. However, there are similarities in the way that neurons in your brain are created or work versus neurons in the deep learning sense. So you'll see the key concept here is neurons transmit and process data. All right, and then transmitting information from one neuron to another is obviously how our nerve cells work. You'll see this teal neuron at the top is sending information to a target neuron at the bottom. And then, of course, one neuron can send information to multiple neurons, the receiving neurons or the target neurons. All right, so the whole point of going through this hack of a biology class tutorial is neurons are similar-ish to a concept of network of neurons in deep learning. So let's deconstruct an artificial neuron. So there's this concept known as artificial neural networks. And within an artificial neural network, there is this concept known as a neuron. So we're going to take it really high level here. We're going to deconstruct what an artificial neuron really is. So you've got an input, you've got two inputs, you've got a weight. We'll talk about what weight means later. You've got this function, let's just consider it, keep it as a function. And then you've got a weight at the end, and then the end is a result. And then I'm sure, as you could tell from the previous slides, the end result is passed to other neurons, right? So formally, an artificial neuron consists of connected neurons that get a set number of inputs and a set number of weights. There's a container around this artificial network, this artificial neuron, also known as a layer, and we'll get more into detail what a layer is, that receives weighted input and then transforms it and then passes the value into the next neuron. And this transformation is done based on the weights and the function that's kind of in the middle, which in a neuron that's similar to the brain would be somewhat like the nucleus. All right, so breaking it up a little bit more and making it sound even more basic, the connections in neurons are considered to be the dendrites. The activation function is similar to the nucleus in the human nerve cell. And then the axon is responsible for the output of the connections. So kind of similar to a nerve cell, kind of not, as we keep getting more detailed about this. All right, so again, an artificial neural network now consists of artificial neurons. So an artificial network is a computing model that is made up of individual nodes, also known as neurons, arranged in layers. We're going to talk more about layers. Layers is a key concept and kind of is why deep learning is called deep. So each node or neuron takes data from nodes in the previous layer as input. After performing some sort of operation on the input data, the node returns that data and then passes it to a neuron in the next layer. All right, so let's talk a little bit about a classical neural network. So there are definitely many forms of a neural network, and I'm talking about it in the most basic form. But a classical neural network is fully connected layers. So every neuron in a layer is connected to every neuron in the next layer, similar to how we were showing there were nerve cells that were connected to other nerve cells in another layer in your brain. So the whole point is information is passed along each connection. If a neuron is connected to two neurons from a previous layer, it will have two numbers as input, and then it'll produce one number as output. That's the key to neurons, is there's always one number that's produced as an output and then passed on to the next layer. So let's talk a little bit about layers. Layers are definitely a key concept of neural networks in the deep learning sense. And neural networks are typically organized into layers. It's kind of considered the highest level of building block for deep learning. It's the sequence of data transformations. Again, there's like two kind of key concepts to machine learning or deep learning or AI in general. It's data, and then it's transforming this data to create some sort of program that acts upon new data. So again, layers consist of a set of interconnected nodes, which we've kind of been highlighting before. It's all about these connection and nodes, which each have an activation function. And we kind of portrayed that activation function in the middle, like similar to the nucleus. And the specification of what a layer does to its input data is stored in the layer's weights. So a layer in the simplest form is a container that usually receives weighted input, transforms it with a set of mostly nonlinear functions, and then passes these values as an output to the next layer. Okay, so we're going to break down the word deep learning. Layers put the deep in deep learning. The first layer is called the input layer, pretty straightforward. The last layer is called the output layer, also straightforward. And then all the layers in between are called the hidden layers. The hidden layers are kind of what make deep learning a black box and hard to understand. So deep is a reference to architecture of an artificial neural network and the number of hidden layers it contains. It just gets deeper and deeper. One layer learns from one dimension, then another layer learns from the next dimension, and so on. And now so we took deep, and we understand why deep is in deep learning. Now let's break apart and why is learning in deep learning. So learning in the deep learning sense, is essentially talking about the data transformations of these layers. So there are a couple of key concepts that we've gone over here. We've gone over the simplest, which is a neuron or a node, and then we've organize these nodes into these containers, these layers, and then nodes within a layer do some sort of computation and pass that information to the next layer. So learning is the act of data transformations via learning by exposure to examples of data. Incremental change in weight between connected neurons in a neural network, in other words. Training is something, so it learned, so it's like breaking down what learning means. Training is something, so it learns how to do something. A little bit different than the way we typically think of software engineering, and we'll touch upon that a little bit later. So back to the example of how a neural network is similar to our brain. If we give it data to learn something, similar to how our brain, if we see someone doing something, we're learning something, and then we can then do it too. All right, so now that we've talked about the biology of the brain slightly, we've talked about neural networks at the highest of levels, do we really think deep learning neural networks are like our nerve cells? Probably not, because our brain is far more complex, and neural networks are also far more complex, but they're not complex in the same ways. So now that we know that they're slightly different, we see the similarities, and we see AI is a super hot topic, and it's very easy to tie AI to something. If you flash, the neural networks are just like the brain, people are gonna be like, this is amazing, I'm building the brain. But there are similarities, but there are differences. So if I were to define deep learning, I would say it's a multi-stage way to learn data representation. Let's jump into what that means in a bigger sense. So we have deep learning. Deep learning falls under the big bucket AI. We all hear about AI. In all seriousness, it's an ancient and broad term. It's something that's been around forever. In a formal definition, AI is the effort to automate intellectual tasks that are normally performed by humans. Again, so this isn't anything new. If we think about it, it kind of originated back in the 1950s when computer scientists and researchers wanted to figure out, can computers be made to think? So if anything was made or tried to apply to make computers think, it fell under the artificial intelligence bucket. So why am I talking about this now? Why did I just switch from neural networks to deep learning to AI? Well, deep learning is a subfield of AI. But before we get to deep learning, let's talk a little bit about machine learning. So machine learning is a program that is trained rather than explicitly programmed. So emphasis on explicitly programmed. We'll go a little bit into detail when we talk about traditional or classical programming. But in a nutshell, machine learning is the training a program by giving it examples of what is expected. The goal of machine learning is to automatically develop models just by exposing it to training data. Training data sets are super important. If your training data set sucks, your model will probably suck. And we'll go into more detail on that later. All right, so this whole concept between traditional programming versus machine learning. Why I've underlined or emphasized traditional and the word explicit in the previous slide is as software engineers, we've written a ton of these. Everyone at some point has written a traditional program. If we're real software engineers, we write traditional programs, and then if we're lucky enough, we get to also work on machine learning, which I think is the more interesting side of our software engineering careers. Okay, so explicitly define what the program does with the data. That is what classical programming is. That is what we're all known to do, what we're all really good at. So you take in data, you create some manually curated rules, which is business rules or just some logic. You apply the data to that logic, and then you create a program, and then the end result is the results that are a result of your program. Pretty straightforward, we get it. It's nothing magical here. Now, comparing to machine learning and how that differs between traditional programming is machine learning discovers rules to execute a task, given examples of what is expected. So you give it data, you give it answers or results, you feed that into your Python script of some sort, and then the end result is a program which you can act upon. It's a program that essentially you can feed it new data, and then it should give you an answer. Whereas before, you kind of used your program for that in the traditional programming sense. An example of this is the easiest example that I can think of is that whole shtick that they did on Silicon Valley, where they built an app and it was hot dog versus not hot dog. They utilized machine learning for that. They created a program, or they wrote some code that had to be trained on images that were hot dogs and not hot dogs, and the end result was an app that could identify a picture that was a picture of a hot dog or not a hot dog. So in a nutshell, that's machine learning in its most basic form. So let's get into what deep learning is. So deep learning is a subfield of machine learning. In deep learning, everything is a vector. Everything is a point in geometric space. Models are long chains of geometric functions or transformations that map one vector space to another. So for example, mapping one data point x to another y, assuming the existence of a learnable transformation from x to y. All right, so let's take a break for a little bit and just kind of summarize what we know so far. Neural nets are kind of similar to the brain, kind of. Deep learning is all about neural networks. Neural networks are organized in layers. These are the containers that hold the neurons or the nodes. Neurons and nodes, the result is some some information or some data point that is fed into the neurons that it's connected to in the next layer. And then deep learning is a subset of machine learning. So there is an aspect of training, evaluating, and deploying models so that these deep learning models can actually have impact in the real world. So yeah, how can deep learnings be applied in real life? So that's kind of what this whole talk is about. But you had to know the basics of what deep learning is and what machine learning is and how that can be applied. Well, how we apply it at Comcast is we build recommendations engines. So recommendations engines can vary between content-based, collaborative filtering, or if you're very legit, it's a hybrid between the both. Content-based methods rely on similarity of item attributes, and then collaborative methods calculate similarity from interactions. I would say recommender systems are one of the most successful and widespread application of machine learning technologies in content discovery applications. It's just the easiest way. We have so much content, and if we have so much content, how do we get the best content in front of you? We utilize recommendations engines. And then, of course, deep learning is able to effectively capture the nonlinear user-item relationships. So, for example, and we showed this example somewhat earlier, let's say I watched Crazy Rich Asians, and I would like to see content that is similar to that specific item. I could utilize a collaborative filtering model that would return movies that are similar to Crazy Rich Asians. All right, so how do we really build neural networks / recommendations in real life? With a lot of data and a lot of engineering, and this is the part that I think that always it kind of gets hidden. So we hear a lot about AI. In the news, we hear a lot about AI on commercials. I mean, there's literally a Microsoft commercial that I feel like gets aired every hour or so where Common is talking about how Microsoft uses AI for this and AI for that, which is really great. But the engineering is never really highlighted, and maybe because I'm an engineer, I think about these things. I'm not a researcher. But I don't understand is there's the aspect of utilizing a machine learning or deep learning model in production. The biggest part of that is all the data engineering and then the engineering to actually serve those predictions in somewhat real time. That's way bigger than the little piece that is the actual machine learning model. All right, so let's talk a little bit about a machine learning system. So this is the simplest form of a machine learning system. You get the raw data. Let's say you live in a perfect world and you don't need to manage that data, and this data is just readily available for you all day, every day. And then you have your Python script of some sort that, maybe it's TensorFlow, maybe it's Keras, whatever you want. It consumes this data, and the end result, obviously there's a lot more details into that, but the end result is predictions. It's the most simplest form of a machine learning system. Probably this is also the most common form of a machine learning system that actually gets deployed to production. And I think a lot of that is because a lot of organizations or a lot of teams get excited that they can utilize AI to solve some problem. So they have a researcher build something real quick, and then they make the poor engineering team support it somehow, and then it's like one of those games where you're always bopping the gopher. That's what it is to deploy this type of system. There's always some problem in there. So the real goal of a machine learning system is to build a solution that's not the case. So it gets a little bit more complicated. So let's say you don't live in a perfect world, and you have to build your data collection pipeline or your data platform. So that's where you take raw data, you consume it from wherever it's available in your organization, and then you turn that into feature data sets. Feature data sets are usually typically what models are trained and learned against. So then once you have that raw data, you train your model on the components learned from the data sets collected, and then you evaluate that model to make sure that what your model is producing is in fact legit predictions. And then once you've developed a proper model that you think can have some impact in production, you make models available such that it can be used to serve predictions. And then, of course, you monitor those predictions to prevent staleness. So there's two aspects of evaluating your models. There's the offline evaluation, which happens in the step before. You train your model. You want to make sure that it's actually producing the predictions that you want. And then as it's in production, you want to make sure it's continuously producing the predictions that you want, and that's when you monitor it in the online sense. And then, of course, you have your infrastructure, so you can't forget about that. Machine learning requires high-performance hardware all the time. So many times there have been cases where the hardware doesn't meet the criteria that the machine learning platform requires of it. And what happens there is then there are shortcuts taken. Shortcuts meaning you feed your model less data so that your model doesn't take as long to train, or you concatenate your data, but then that means you lose some of your data, which means your predictions won't be as good. So the goal of a machine learning system is not only to incorporate raw data, feature data sets, a pipeline for model training, and then a pipeline for serving predictions, but also proper infrastructure to handle all those key components. And then the last piece of a proper machine learning platform is a workflow engine. So all of these tasks need to happen. All of these jobs need to run against the raw data set, create a feature data set. The model needs to train. We don't actually want someone to sit there and watch for the training data set to be done and then, trigger the model to train and then trigger the evaluation metrics to run and then trigger the publish of the model, of course, and we're not going to just select a hacky cron job to do that. So that's where workflow engines come into play. Workflow engines help managing and scheduling of tasks. Okay, so this is the bigger picture of everything. This is the whole point. I tried to make this overwhelming because there's a lot that needs to happen with machine learning beyond the AI, beyond the actual model that's created, which is typically the first step. Well, the first step in an ideal world is you find the data. The second step is then you build a model that could use that data, but usually it's reversed. Usually researchers or data scientists start experimenting with a model, and then the next questions after they've gone to some extent, some point of experimentation is, well, I need this data set, and I need this data set. And then you kind of get into this place where you're pulling in data sets that you can't really support just to make the model better. So there's a lot that's involved in building a proper machine learning system. All right, so let's start talking about the challenges of deep learning. The struggle is definitely real, it's legit. So deep learning is hungry for data. Deep learning requires vast amounts of data. It's just the more data you feed it, the better the predictions that will be a result of that deep learning model. So it works best when there are thousands or millions or even millions of training examples. So what happens when a deep learning algorithm doesn't have enough quality training data sets? That means that the predictions that it's producing is not as adequate as it would be if you gave it more data. All right, so deep learning is also expensive. What I mean by that is because deep learning requires highly parallel computation resources, it requires high performance hardware, and high performance hardware like GPUs gets expensive. And then of course these are when shortcuts are typically taken. So if we take a shortcut on the data, so let's say we feed the model less data, then that means we don't have to spend as much money on storing the data, which means that our models are quicker to train, so we don't have to allocate as much resources for the action of training the model. That means we save money. But overall, saving money and saving resources by not storing as much data, does that really get us the impact that our models should serve? And then last but not least, deep learning is kind of a black box. And I think this is the part of the talk where I could just kind of go into this rant about how a lot of times there's a good idea that can be solved with deep learning or AI, but sometimes if you make it more complex, you're adding a lot of obscurity that makes the end result kind of fail. So the hidden layer within all of this is that this is really complex. When in doubt, try to take the complexity out by actually building a proper engineering platform to support the complexity that is machine learning. Reasons for deep learning somewhat being connotated with the black box syndrome is that the layers in the feature extractions take place are kind of obscure. So the number of hidden nodes, the number of hidden layers are arbitrary for the most part. So every hidden layer extracts features that helps in identifying like an image or an item to similarity association. And if you're classifying those, it's hard to actually get in the granularity when you're trying to debug things. Having said all of that, there's this really good paper written by some ex-Google developers. It's called The Hidden Technical Debt of Machine Learning. One of the reasons why I pretty much always present on this or always include this, this specific diagram in my talks is that it perfectly articulates the black boxness of machine learning and then also portrays everything else that's needed that's far more vast and complicated typically. So you'll see right in the middle is this little black box. It's the actual machine learning code. It's the Python or whatever. But then everything around it is needed to make that perform in some fashion. So long story short, there's so much more to AI than the actual model. There's infrastructure, there's data pipeline, there's workflow engines, there's model serving. There's a lot more that's needed to be able to facilitate the details that are needed in producing predictions via machine learning platform for your production, for your customer-facing products. All right. I like whizzed through that. Any questions? I have to switch to, yeah.
How often does the model need to be updated?
That's a really good question. It kind of depends. So that's something that should go into account when evaluating your model. It's how quickly do you want your model to make a change based on new data. So it depends. I mean, the frequency in which you train your model can be based on how much data you're consuming between the last time you trained it versus the current time, and then how much resources you have to be able to frequently retrain that model. Yep.
And the neural network develops its own weights.
In the hidden layers, it starts developing its own weights, correct?
Those weights have to be stored, and
They're encoded. They're in the encoding layer. And I think that's where it starts to become like a black box, because you're not exactly sure what those weights are. If that makes sense.
you can look at it and see.
You could like iteratively go through it, and this is something our researcher, the researcher on our team has recently done. She iteratively went through how we were building the similarity matrix, and what we noticed was it just kept getting larger and larger, and we're like, this is not the solution because we can't store this large similarity matrix in memory. But you can iteratively go through it. It's not ideal. So the number of times you like reprocess data is called an epoch or an epoch. The more times, typically, you train it to the point where you start seeing degradation in the metrics that you use for evaluations. So sometimes a model could be trained like 50 times over the same set of data with slight transformations as you go through the process. So think about 50 times manually seeing the weights can be heavy. Yep.
Yeah, so my question is regarding the data. So you did mention that there's a lot of data required, which we understand. But for a perspective, from your experience, is there a difference between the data required for the implicit recommendation and the explicit recommendation? And what is the scale, just to give us an idea of how much data we need?
So the way we break it up, at least at Comcast on our personalization platform, is the data that's used for deriving the features that are known for explicit personalization are the same signals that are fed into our implicit platform, or our recommendations algorithms. It's just there's a variation in how much data is used where. So explicits, we typically only use like your last n months, where your implicits, we should train it in your last like 2 years worth of usage history. So it just depends. I think that's also an art with personalization, is when do you invoke like your most recent usage to portray like features on the platform, on your content discovery platform, or when do you invoke historical usage?
And the data is specific to the user or the...
Yep. Yep. To the device.
How do you actually test this with the data model?
How do I actually test the data? Sorry, can you repeat that?
How do you actually test the data model?
Okay, yeah. The question was, how do you actually test the data models? Test the machine learning model or the data that we're consuming?
The data model, like the data layers.
The data layers. Okay, so I think you kind of you test it via the outcome, sort of. So you test it via the predictions that it produces, and then you evaluate those predictions based on a slew of metrics. So the most basic form is this concept called recall. So essentially what you do is when you train your data model, you keep some portion of your data set aside for testing and evaluating against. So let's say you have like 500 records of what you've watched on TV. Just keep like a portion of those, like 10%. Train the model on the test data set, and then once your model is trained and produces predictions, then evaluate if your model would have predicted that we would recommend this TV show by checking the evaluation data set, if that makes sense. It's just in a nutshell, it's partitioning your data set between test and evaluation. Yep. Oh, it's working now. I'll just real quick. Hey, what's up?
As machine learning and these deep networks become more obfuscated black box, how can these developers be proactive about the ethics of the content that we serve through these recommendation networks?
That's a good question. Yeah, I don't really know how to answer that. The ethics, So I think recommendations is a little less harmful in the ethics world because we're just trying to recommend content, and obviously it's like it's appropriate content. But yeah, I can't really. I'm not really quite sure how to answer that, but I know where you're going with that. So I'm going to try to use this thing. So what is the weirdest thing your AI learned at Comcast? One of the engineers on our team, he did do some analysis on clustering users. And so we did find what people liked to be interesting, like people who watched more conservative TV shows watched another interesting genre, or people who watched more liberal TV shows watched another interesting genre. So it's kind of seeing what, I think the most interesting part is how to utilize clustering and then enabling those clusters, those groups of customers, and then training your models on those group of clusters. I think that then we would see more interesting outputs. So yeah, how much processing time is spent per customer for recommendations made? With our current implementation, not much because we're incrementally building a similarity matrix. So this job runs every day and creates this large similarity matrix, and the similarity matrix is kept in memory. And then on request time, when we're trying to surface recommendations on X1, what we do is we first invoke a request to get all of your usage history, and then we look at the similarity matrix and then the list of content that we're working on reordering, and we take those three pieces and then reorder the content based on your taste profile. So processing time for that, I'm not quite sure what the SLA is, but it's enough where no one's noticing it's an issue. So go ahead.
How do you deal with the corruption? Like example recommendation.
Mm-hmm.
I would be on look at a certain TV show.
Yeah.
And my daughter would come on and she'd be looking at totally different TV shows.
Yeah.
So all of a sudden there's a recommendation.
Yeah. So other content discovery platforms solve that by profiles. We don't do that at Comcast. I think the most elegant way to, that's obviously going to be noise, and you have to see how heavy that noise is. So if your daughter's consistently doing that, it's going to play a heavy role in your recommendations. If it's not, it's like if she just does it once or twice, it's not going to be enough to really change your taste profile. But I also think a more elegant solution to that is just the concept of day parting. So let's say you live in a household and every day your kids come home and they watch TV from 3 to 5, and then you watch TV from like 7 to 9. The recommendations that are served between those parts of the day should be different. But there has to be a consistent pattern to be able to do that. Okay. Do you rely on cloud infrastructure for training models or on-premise? We're in a balance of both worlds right now at Comcast. So we have some of our platform that's on physical hardware that we're actively trying to move up to the cloud platform, and then anything new that's developed is in the cloud, is in AWS. I'm sure we'll be going back to physical in like a few years, and then they're going to make us go back to cloud. How do you develop features for a model to learn on? That's a really good question, and that's actually usually the issue that we run into most, is that we don't have enough labels on our data sets. So I think labeling data is something that could also be talked about, but there's just not enough time to talk about how the art of labeling data and the art of having that data set already labeled for you when you get to the point of creating your machine learning models. But yeah, I think so some people have a actual human that's hand labeling them. Some others build a Spark job or a Flink job that adds these extra labels, like a rating label. So for example, a label that we could use is how long you've watched something. So if you've watched something for the entire duration of how long the TV show was, that's a very strong label. We could say you've rated that 1 out of 5 of 5. So that's like an implicit form of a label. Another label, and I think Netflix used to have this, was this like thumbs up, thumbs down field. All right, so how do you measure the lift of the recommendations engine? So I think that means, I'm not quite sure what that means, but I think what the impact of that recommendations engine is compared to other models or compared to like utilizing popularity or editorial. And I think the best way to measure any impact of your algorithms is to do an A/B test, and then obviously compare what the lift of the control is versus what the lift of the test group is. I'm not sure if I answered that one correctly though. And then, what is the source of prediction data? I don't know what that means. Go ahead. Okay.
So I meant, like, for X1,
Mm-hmm.
the predictions you make
Mm-hmm.
are relative to what the existing data input.
Mm-hmm.
So how do you get the predictions data set from? Like, what is the source of it?
Like what's the source of our like how our data platform looks?
Yeah,
The source of
the input is crazy situations.
Yeah.
You get the predictions from another source.
Mm-hmm.
The related
Mm-hmm.
situations. So how do you get that?
I guess it's just based on user actions. So like what you've watched or what you've clicked on or what you saw but you didn't actually,
Yeah, so those are the triggers.
Right.
How do you get the actual data?
the action data.
Actually.
The actual, like how do we actually consume this data? Okay, so I think there are various ways we consume the data. I think some data we consume from Kinesis, some from Kafka. I don't know if this is route where you're going, like how our data platform looks. A long time ago, we used to disk copy from one cluster to another. That doesn't exist anymore. But yeah, I think there are various ways we consume data. For the most part, it's between Kinesis and Kafka. Roughly how many hidden layers exist in an average deep learning neural network on a Comcast recommendations engine? That's a good question. I actually don't have the answer for you right now because we're currently evaluating one of our deep learning models to hopefully replace our collaborative filtering model. I can tell you though that so far, based on just the training data sets we've fed it doesn't look as heavy. From a engineering perspective, storing this model doesn't seem as heavy as storing the similarity matrix in memory. But that doesn't really answer your hidden layers. I don't really know. And then, does your TV recommendations engine do any learning from internet usage as well, or is it strictly based on TV usage? That's a good question. They're separate. So it's based on the device ID. So based on what you watch on your web mobile device, on your stream device, there's a device ID correlated with that, and then there's a device ID correlated with your TV device. It would be interesting to, if we ever get to the account level recommendations, is sharing that across. But I think for now, device level is the best we can do without invoking profiles. Removing. What are other use cases of deep learning other than recommendations? Similar to machine learning, so there's image classification, there's utilizing deep learning in the NLP world, so that's something like creating like the voice remote being able to understand what someone's saying and then interpret that into an actual action to be invoked based on the customer's command. You can also utilize deep learning for creating topics. So an example of a topic is, let's say you have, this isn't recommendations, but this is more creating different types of content that surface to you. So let's say you have drama and you want to create subgenres, you can utilize deep learning to do that. So then instead of having just this one row of drama for you, you have more granular dramas like, I don't know, really intense dramas, scary dramas. Which framework are you using for deep learning, TensorFlow or something else? Right now, we started with TensorFlow and we're moving towards Keras because it abstracts some of the guts of TensorFlow for us. So yeah, Keras. What resources would you recommend to someone, primarily noobs like me, who want to learn more about neural networks, machine learning, and deep learning? There's this thing called Kaggle, which you could look into. There's a lot of good examples, and I would probably not start there. But also, when I switched over to the recommendation/personalization team, I started looking at how other companies were utilizing recommendations. So obviously, I started with Netflix, Uber. I mean, Uber has great documentation on how they build their engineering platform that facilitates all the steps that I kind of outlined. I think it's called Michelangelo. This is the other aspect of machine learning, is every big company is doing it their own way. Facebook is doing it slightly different than Uber, definitely different than the way we're doing it, different than Apple is doing it. So I would start with examples of how other people are utilizing these frameworks and these tools. And then I usually try to reverse engineer that or start from the basics and just start reading. I mean, there are a lot of good in-action books that touch upon deep learning. And then last question, or not. If the source of the data is user actions and the output drives user actions, does that create a feedback loop? It definitely does, and that's definitely something that always to take into consideration is the feedback loop. It's really important. You can definitely you can start creating bias depending on how you're utilizing your recommendations on your content discovery platform. What factors are causing you to switch from TensorFlow to Keras? I think for the most part I think TensorFlow is really good from a research perspective or a data science perspective, but to really build something that's maintainable and that's less of a black box, abstracting some of those APIs and some of those methods and utilizing something like the Keras library just makes that model have hopefully a longer longevity in production. I think that's kind of the problem with machine learning is it's really easy to slightly change something, and then if you're not evaluating or monitoring how your machine learning model is being used in production, it's really easy to mess something up, which is not really the case with traditional programming. So yeah. Can you speak to which cloud platform services you are using for your machine learning needs? Yeah, so we're in AWS. Like I said, I'm pretty sure we'll get kicked out of AWS at some point. I mean, so from a managed services perspective, our new goal is to not rely on managed services so that we could easily jump to a different cloud provider if we need to. I mean, obviously there are exceptions to that, like Kinesis. If the data team's sending their data to Kinesis, we need to read from Kinesis. We can't just ask them to stand up a Kafka cluster for us. And then for our machine learning needs, we're still experimenting with the best way to invoke the inference layer such that we can actually utilize the deep learning model in production. So I'm not sure exactly where we'll go there, but I do know that there are a lot of tools that could help with that. But that's to be continued. Have you considered using SageMaker? We looked into it a little bit. We also looked into AWS's personalized service. I think I'd rather just build it in-house, but I think any engineer would say that. All right. And then how do you choose the size and type of the model? There are so many types. How do you pick the right one? Yeah, you just keep evaluating. And you also consider how hard would it be to support this in production? That's super important. I mean, sometimes there are some hits that you can take just so that it's not a mess supporting this model in production. But yeah, I think the thing that's hard about being on a recommendations or personalization team is it's not like traditional code or traditional engineering or classical programming. A lot of what you do probably won't see the light of day. There's a lot of experimentation and evaluation, and there's a lot of time spent like not knowing if what you're going to do is actually going to make it to production. So I think it just takes patience and obviously experience. Like if you get to work with an experienced researcher who doesn't start with mistakes that a new one would, that helps. Is your model better than editorial or popularity lists? How do you measure better? That's a good question. I feel like I asked that one. It depends on where the algorithm is being utilized. For the most part, how we measure is via A/B testing. But if you think about it, editorial, it's like one size fits all. Everyone gets the same thing. Personalization/recommendations, it's more geared to your tastes. So naturally, it should be better if you have a somewhat good algorithm. And yeah, how we evaluate that is usually with A/B testing, or it is definitely with A/B testing. All right, last question for reals. Besides setting aside data for testing, do you evaluate your model based on engagement metrics? Yes, and that's more in the online. So there are two ways, I kind of spoke about this earlier. So there are two ways to evaluate your machine learning models or your deep learning models. One is in the offline sense, and that's where you set aside that test data set and you evaluate your predictions against that test data set. And then there's continuously monitoring how your model is performing in production. And that's when you've gotten to the point where you've published your model and then you're actually serving predictions from that model. Some of the engagement metrics that you could evaluate is every time that row is surfaced that's utilizing the model, what's the click-through rate, what's the watch rate, simple things like that. Based on how many impressions of that row has been seen, has there been a lift in consumption because that row is all of a sudden there? So yeah, definitely +1 on the engagement metrics. That makes those something we do. All right, thanks everyone.